So Andrew Granville is best known for his work with sound, developing the pretentious approach to number theory, and I think he's describing some of their work as well as some more recent developments today. So you're welcome.
Okay, thanks, Kaiser. Well, it's nice to be back in Finland. I was in Finland this time last year. I shared part of my sabbatical in Turku with Kaiser and her team. It was a lot of fun. And I'll describe some of the work in here that we did together. I was just saying as we logged on that I was missing some of the Finnish food. I've managed to get a decent salmon soup, but I think that's about it that I can imitate from my time in Finland. So in preparing this talk, I was just trying to decide, you give a colloquium to a broad audience, you have to decide what you're going to say and how you're going to say it. And, Finland is, I guess, more famous for its analysis and number theory, perhaps. So I'm going to make more assumptions about your knowledge of analysis and your knowledge of number theory. I hope that fits for most people. Certainly looked that way in the Turku department. So, but let me start from famous question on counting the number of primes up to a point. And this obviously is a question that goes back to antiquity. And the young Gauss, when he was 15 or 16 years old, he counted the number of primes in intervals of length 1,000. So where I have m equals 0 here, it's from 0 to 1,000. This is number of primes from 1,000 to 2,000. This is from 2,000 to 3,000. And this is the raw data, which actually didn't have precisely correct, but close to correct. And the question is, can you model this with an approximation? And what this teenager did was he said, that looks to me roughly like it's the inverse of a natural logarithm. How a 16-year-old would have thought that. It defies imagination, but he did. We know that one of the few books he had actually was a table of logarithms, but not the inverse of logarithms. So it's very strange that he came up with that. So let's just have a look at, here we go. So that was what he guessed. And then let's just compare it to his guess with what it means. So he would approximate, for instance, between 2 and 3,000, that using this integral formula, well, obviously it's not an exact integer, so I rounded it to the nearest integer. His guess would have been 128 primes, and it's actually 127. Well, you can see once you get past actually the first interval, they're all amazingly good approximations. So 16-year-old Gauss said, I know I've hit it. I know that's good. Okay, so let's just have a look with modern data. So what you can see here is various values of x. I sort of cut some powers of 10 to start to fit the slide. The number of primes up to x, and then this is called logarithmic integral. It's integral dt over log t. So that's kind of the way to approximate 1 over log x being the density. And what you see is that the approximation is very good. I mean, if you look at this column, the error term, if you like, when the Gauss approximation, it's about half the width of the column of a number of primes, right? So it appears that the error is roughly square root. In fact, if you look at what happens as you go from, say, 10 to the 25 to 10 to the 27, it's about 10 times larger there. So as you skip up 100, a factor of 100, you multiply the error by about 10. So it suggests several things. Firstly, that the error is about square root. You can see that all the way along, by the way. If you go up by 100, the value, then it's a little under 10 that you multiply by. So even maybe less than square root x. So this data seems to suggest an error term about square root x. It seems to suggest it's always positive. The latter one's a little misleading, but I'm not going to talk about that. But square root x is worth remembering for this approximation, what seems to be the error term. So once you make this guess as the number of primes up to x, and you want to prove it, and the question is, how do you prove it? Well, the one thing I'll say is that trying to understand this integral is difficult. I mean, if there's no particularly good approximation to it, you can integrate by parts and get a series, but it's not a series that actually converges if you take the infinite series. So you can only approximate this integral by finite truncations of a series. But what makes a lot more sense is if you think that the probability of random integer being prime is 1 over log, then maybe if you put in a weight log at each prime, life would be less complicated. And then in that case, you have sort of an expectation that each integer contributes 1. It doesn't really make sense, but what you're sort of saying is there's in a short interval around x, you expect the length of the interval divided by log x primes, and if I weight them all for log x, then I'll just get the length of the interval. So this is a less complicated version of this, and it's easy to show they're equivalent. We call this the prime number theorem, and it was proved in 1896. I'm going to briefly talk about the proof, but it's not where I want to go. And the data suggests, oh, this symbol means asymptotic, so when you divide one side by the other, the limit is 1 as you go to infinity. But the data suggested this square root x error term. So I sort of use this idea that 1 in log x is prime, and you can make a sort of probabilistic model out of that by just saying, well, look at the set of sequences where n is in your sequence of probability 1 over log n, and each n, it's an independent random variable with that probability based on it, and then you can try and say that's a good model for the prime. So anything that occurs for those sequences should probably occur for the primes. And this is actually in Harold Cramer, the famous statistician. His PhD thesis talked about this, using Gauss's idea to create a model and to make conjectures about primes. And then when you do that, you get a normal distribution for the number of primes up to x. And so with a normal distribution with x elements, you recover an error term something like root x. I mean, it's like root x over log x or something. So that's not where we're going either, but I thought I'd mention it. So the reason the prime number theorem is still celebrated as a theorem is that it's not easy to prove. Today, there's quite a few proofs. There's probably 8 or 9 proofs, but none of them are trivial. And I think fundamentally, it all comes from the problem of how you define a prime. It's something we don't think about a lot in math. We tend to think, well, we have a definition that's good. We're good. But when you define a prime, you don't actually say this is a prime. You say a prime is something that is not the product of 2 integers greater than 1. So it's not actually defined by what it is, it's defined by what it's not, which makes it a little difficult to find a way to kind of really get hold of them. So the way we tend to get hold of them in classical analytic number theory is quite a tricky idea. And it comes out of this formula of Euler, who decided to look at the sum of 1 over n to the s. He actually only looked at it for s real, but the same arguments work for a real and greater than 1, but works fine if it's a complex number of real part greater than 1. And from the fundamental theorem of arithmetic, the sum of 1 over n to the s, you can just factor the n's, and then you get geometric series, so you end up with this formula. So Euler played with this formula, and that's not quite where we're going to go. It was Riemann who looked at this formula and said, well, this is actually a nice way to get hold of the primes, because if you look at the product over primes, then it's sort of purely over prime numbers. So what Riemann said was, let's take the logarithm, and then I've got this sum over primes or prime powers, right, p to the k to the s, with a fairly simple weight. And maybe I can extract some way of estimating the number of primes out of this by using calculus. So there's this formula, actually, Perron's formula comes later than Riemann, but essentially Riemann used a formula that's very similar to this. And the point is, if I want to count the primes up to x, then one way of thinking of it is I want x over p to the k to be at least 1, right? So that's the same as saying log x over p to the k is at least 0. So what I want to estimate the sum here is a formula that gives me a 1 if p to the k is less than x and a 0 if p to the k is greater than x, and then I can sum over all primes. And then Perron's formula allows you to do this. And so, well, I'm not going to do the work, but if you put this formula into here and get rid of p to the k less than or equal to x by using this formula, then you end up with this. So this is Riemann's brilliant insight that he could count the number of primes or prime powers up to x, but the squares and the cubes, there's very few of them, so it's essentially counting all the primes. He could just do a little bit of magical calculus on this, and then he could count the number of primes. Well, the problem is, it's not so easy to do calculus on this. And the obvious way to do it, complex analysis, is to shift this contour at the line 2 far to the left. So, I mean, first you've got to understand the function log zeta s. And in fact, it's not hard to show zeta s is meromorphic, that it has only one pole, a simple pole at s equals 1. But even working with that and trying to push the contour to the left, you have this problem that if I put in say a 0 of zeta s, then it's going to look like s minus r, if r is a 0 around there. And log of s minus r is a logarithmic singularity. And if there's infinitely many zeros, you've got infinitely many logarithmic singularities to deal with. So it's not going to be fun. Actually, that is what Riemann did in his famous memoir in 1859. He does work with his formula, and he acts like it's easy, but you know, the devil's in the details, and he gets them all right, but oh my, it's hard work. Today we have a better idea actually of doing this, so it's a bit easier, and it's very simple. We just go back to this formula for log zeta s, and we take the derivative. So zeta prime over zeta, and then here we'll see the derivative gives us a minus log of p to the k. So when I put that into a formula over here, I get zeta prime over zeta. I'll put the minus sign on the other side, is this. Now, when I do the same thing, what I get is, well, the zeros and poles of zeta are just poles of this function of zeta prime over zeta. So now you're just dealing with analytic functions, and the world's an easier place. So this is the modern way of counting the primes. And the main thing to notice is there's a simple pole s equals 1, and that gives us an x term, easily enough. And then all of the zeros gives us, when you plug it in and you think it out, x to the row over rho, and then there's just this little pole at s equals 0 for this extra term. So it's strange that you get an exact formula here. I mean, assuming convergence and you can pull the contour and you can understand things well enough, but you can. So you get an exact formula for the sum of log p, and once you've got that, you can deduce a strong form of the prime number theorem. If you look at this, and let's not worry about how many zeros there are. In fact, in order to prove something, you're going to have to. But the main thing is, how big are these terms as x grows? And the x to the row, what's the size of x to the row? Well, it's x to the real part of rho. And so you expect this sum to be as big as the largest term, which is like x to the real part of rho for the biggest 0. So we're going to get from this argument, in fact, it's really a proof that the sum of log p, and in fact, we'll get the same estimate for the number of primes, is x plus an error term, which is x to the power, the size of the biggest 0. Of course, Riemann conjectured the biggest 0 lies on the line of half, the biggest real part of a 0. And so that makes the error term in the prime number theorem about square root x, and then there's a nice argument that makes that if and only if. So in fact, it's a rather interesting for this talk is that, I mean, the way I like to think about it is the prime number theorem is an elementary question. How many primes are there up to x? And then Riemann came up with this magnificent idea of building an analytic continuation, studying its zeros. It's a complicated function. And he brilliantly made it work, or wrote out a plan that other people made work. And at the end, what's sort of extraordinary is that, okay, the Riemann hypothesis tells you what you get from the data, that the prime number theorem and an error term that's remarkably good. And here's the crazy bit, is that if you get this error term that's remarkably good, you get the Riemann hypothesis. So there was a view in mathematics in the 1900s, early 1900s, that you couldn't give an elementary proof of the prime number theorem because this is an if and only if statement. I mean, proving a strong error term about the prime number theorem gives you the Riemann hypothesis, gives you something about the location of zeros of an analytic continuation. So It turned out not to be right, that thinking, but it's very persuasive thinking. So the best unconditional work is simply we somehow extrapolate information we have about zeros from the right of a line 1, where it's absolutely convergent, to the left as far as possible, obtain a zero for region, and get some sort of error term. We don't really have a method of working with any of the analytic continuations of zeta that gives us zero-free regions. So what I want to say is the thinking's a little bit wrong in some sense that you have to think about the analytic continuation of zeta. This is sort of a start of where I really want to talk about. So I'm going to show you a formulation of the Riemann hypothesis that lives on the right of the one line. So that seems a bit unlikely that we're taking analytic continuation of zeta, and what we're saying is it has no zeros to the right of a half, or all of the so-called non-trivial zeros are on the line a half. Now, okay, so let me just transfer the statement to this statement. So I said there's only one pole. So zeta prime over zeta, the poles of that are going to be the zeros and poles of zeta. So if the zeros are all to the right of a half of zeta, then in here, they're not relevant to the right of a half. So the only possible pole of this function is going to be a pole of zeta. And I said there's only one pole. It's a simple pole, s equals 1. And adding this term in cancels that pole. So actually, this function is analytic in there is equivalent to the Riemann hypothesis. I mean, it's not a very hard step. It's just that you just have to account for the one pole. So we're still to the right of a half, but here's the thing that's sort of amusing is if I look to the right of 1 and I can build a Taylor series everywhere to the right of 1 that has radius of convergence a half, then I'm good. Because look, if I take, oh, this should have been equal, I'm sorry. If I take a point at a real part of half plus delta, then I take a point to the right of a half at 1 plus delta, and then these are less than a half apart. And so if I can build a Taylor series at S0, then I will get a definition for the function at a half plus delta, and thus I have an analytic in that region. And of course, if I'm talking about Taylor series, all I really need to do is bound the coefficients of a Taylor series. So this is a formulation that's of a Riemann hypothesis that's I mean, so I should say this direction is what I just proved, that if you have bound on Taylor series and you have this radius of convergence, the other way is a little more involved, but it is if and only if. So what we've got is a formulation, completely elementary formulation. Just write down the coefficients of this thing and show they don't grow too much. And if you can do that, you can prove a Riemann hypothesis. In fact, my colleague Dimitris Koukalopoulos proved this with 2 and replaced by log of the size of S0, and then something slightly less. So he actually recovered the best results that are known on error terms in the prime number theorem, or zero-free regions, using deep ideas about zeta functions. It turns out you can prove exactly the same results by bounding the coefficients to the right of 1. So we're in an odd place with this, that the sort of stuff that was considered not long ago to be quite deep and inextricably connected to the zeros of the Riemann zeta function are nowadays nothing to do with the zeros of the Riemann zeta function. Turns out they're about coefficients of a naturally defined series to the right of 1. So it suggests that there are elementary ways to attack a lot of analytic number theory. So let me give you one more elementary way. It is connected, but I can't really get in. I haven't got time to get into all the connections. So I'm going to count the number of prime factors of an integer, omega n, including multiplicity. So omega of 12 is 3 because you've got 2 squared, 3 to the 1. And the prime number theorem can actually be formulated as saying the number of integers with an odd number of prime factors is basically the same as the number of integers with an even number of prime factors. And if you get a good error term, so I could also formulate this as -1 to the omega n, because these are all -1 then, and these are all +1. So when I add them, that should be close to 0. So the prime number theorem is the same as saying this Liouville function, this -1 to the number of prime factors, has mean value going to 0. And in fact, the Riemann hypothesis is that it grows less than x to the half. So I should say lambda n is an example of a multiplicative function, that when you take lambda of a product of two integers, you get lambda of one times lambda of the other. Formally, multiplicative functions should be their coprime. Let's not worry about that. This is certainly included in the usual definition. So here's the way I want to think. If the prime number theorem is false, then it means, if it's false here, then it means this isn't true. So the mean value of lambda n is not 0 as x goes to infinity. So lambda is an example of a multiplicative function. And what I want to do is think about what multiplicative functions do not have mean value 0. And here's one that's fairly obvious when you spend a little time thinking about it, is if I take n to the it, and t is fixed, x is getting larger and larger, then I can approximate it by this integral with a very small error term. And this integral I can work out exactly. So the mean value of n to the it looks like x to the it over 1 plus it, which one needs a second to think about, is that has absolute value, basically the denominator, the absolute value of the denominator, the absolute value of the numerator is 1. But the interesting part is as x grows, it rotates around the unit circle. So strangely, this mean value doesn't tend to a limit. It does an absolute value, but its actual value rotates around the circle. So here's an example of a multiplicative function that doesn't have mean value 0. By the way, if I take t equals 0, that would include 1 is a multiplicative function that doesn't have mean value 0. And I could ask you, and it would be easier if we were all in a room together. So I normally ask for volunteers at this stage, but maybe I won't do that, is whether you can think of any other examples of a multiplicative function that doesn't have mean value 0. Give me a second to think about it. Well, I mean, it's sort of a mean trick, is that if I took the function that's always 1, except that I made it minus 1 just on 2, then I could get something that's not got mean value 0. So what I'm saying is I could take something that like n to the it, and I could change it on a small number of primes. I could change the value from n to the it to something else on a small number of primes. So it's still a multiplicative function. And then you wouldn't expect the mean value to change very much, or it should change in a controllable way. So those are the only examples that you'd be able to come up with of multiplicative functions that don't have mean value 0. It's n to the it or something close to the n to the it. And in fact, this is a theorem of Hollas from 1968. If the mean value is non-zero, then Fn is close to n to the it. And what do I mean by close? Well, this is the formulation that the mean value, forget about this, is essentially less than e to the minus L, where L is this. And the right way to think about this, it turns out now, is that, well, this measures, if you like, if f of p equals p to the it, this is 1, and we get complete cancellation. And otherwise, fp is close to p to the it, then this is small, and if fp isn't close, this is large. And one can sort of generalize this to comparing any two multiplicative functions. P to the it is a multiplicative function. And this distance is something that's used in the modern theory. It satisfies triangular inequality, and it's a distance for all functions with absolute value 1. Okay, so this is what comes out of Hollas's theorem, is if the prime number theorem is false, then the mean value of lambda n is non-zero. This means that this distance between lambda and p to the it is bounded. If I formulate it as before, it looks like this. And well, you can play with that. And the point is you come up with 0 zeta. So if you know about how the prime number theorem is normally proved in the textbooks, it all revolves around assuming there's a 0 on the one line. So there is a connection with this theory with the usual theory, but it's definitely got a different focus. Okay, so I'm going to get into the theory of multiplicative functions a bit. So let me start with this question of if I take multiplicative functions that only take values 1 and minus 1. So for instance, the Legendre symbol, mod p, is a function that tells you, say, mod 7, it's 1 if you have a square and minus 1 if you don't have a square. So n over 7, 1 over 7, 2 over 7, 4 over 7 are 1, and 3, 5, and 6 over 7 are minus 1. So that's, well, that's the slight problem with that is that f of 7 is 0, but one can alter that. But what we want to look up is the family of multiplicative functions where every value is 1 or minus 1. And what I'm interested in is the set of possible mean values. So if it's non-zero, if it doesn't go to 0, Hollas's theorem tells you that f must be p to the I pretentious. So this thing must be less than infinity. This distance must be less than infinity. And in fact, these fp's are all plus or minus 1, so that's the same as saying this is less than infinity. And what would that mean? That would mean that the real part of p to the it would have to be close to 1 or minus 1 for most primes. But if you think about p to the it, it's as long as the p's aren't too widely spread, which they're not, that's going to be rotating around the unit circle, so it's not often going to be close to 1 or minus 1, unless t equals 0. So the only way this could be non-zero, this mean value, is actually if f is p to the it pretentious where t is 0, so f must be 1 pretentious. This means that there's very few values in which it's minus 1. Okay, so I'm going to look at what are the possible mean values of multiplicative function where it's only 1 or minus 1 on the primes. And if we have a function that's 1 or minus 1 on the primes, it's 1 or minus 1 on the integers. So the sum has to be between minus 1 and 1. And what I want to say is that this set of mean values is basically continuous, because if I alter the value of f of, so I could start at 1 by making f of n equal to 1. And then I could change, from one large prime, I could change the 1 to a minus 1. That would have a minor alteration and make things a little smaller. And I could change the values at 1 prime at a time to have little jumps that would take this mean value smaller and smaller and smaller till it got as small as possible. And then if I let x grow, then you can make a continuity argument. You can say that the set of mean values is actually just some interval. So the question is, what is this value of c? In 1996, it was proved that you can't have a mean value of minus 1. So what would a mean value of minus 1 would mean? It would mean that almost all of these hit minus 1. I mean, they can't all be minus 1 because, I mean, f of 1, f of 4, f of 9 would be like f of 4 is f of 2 squared, so it's a square of minus 1 to 1, so it'd have to be 1. But you also have this issue with like f of 6. I mean, if f of 2 and f of 3 are both minus 1, then f of 6 is plus 1. So you guarantee that at least one of those three numbers, f is plus 1. So you have this very tricky thing that it's a bit like putting a too big carpet in a room. If you push down f of 2 and f of 3 and make them both minus 1, then f of 6 pops up as a plus 1. So the question is, how can you organize things to get the most minus 1s possible? And we resolve this with Soundarajan, that's what Kaiser is referring to a bit, introduction, and showed this, as it happens, this constant is some crazy dilogarithm value. So let me show you that it's a very special function that hits that. What's the best way to organize things? It's to make the function 1 for all small primes, and then for the larger primes to make it minus 1. And in fact, for the primes between y and y to the 1 plus root e, you might ask why 1 plus root e, and it's the solution of some horrible differential equation. I won't get into that. But yeah, so we have a very neat answer to a complicated question. I mean, neat in terms of what the function looks like. I mean, this constant is meaningless as far as I know. So once we'd sort of been looking at it, Sound and I, we asked ourselves, could this idea of pretentious distance replace Riemann zeros in, well, I showed you at first the proof of the prime number theorem, standard results in analytic number theory, but also in non-standard, like the result I just presented. There was no sort of general theory. There was a lot of ad hoc results not involving Riemann zeros in analytic number theory, but the question we sort of asked ourselves is, could you prove all the standard results using this family of ideas once we sort of got this head start with the prime number theorem? And by 2019, this has been achieved. That basically all of the standard results in the subject were proved. We worked with younger mathematician Adam Harper, who found a much nicer way of formulating what we've done. And we were able to not only prove all the basics, but some things that are considered very hard. Hochheisel's theorem is about primes and short intervals. Linux theorem is that every arithmetic progression has a prime, or every arithmetic progression A mod Q, where A and Q are coprime, up that is smaller than Q to a fixed power. So yeah, so this, I mean, the dates reflect publication. This in some sense was the first proof that didn't really involve in any way Riemann zeros. But there was another proof around using sieve theory that was very difficult by Friedland and Vanietz that did involve, of these difficult theorems, I should say, that involves Riemann zero, but a bit artificially. But very recently, there's a lovely new proof by three Finns, Kaisa, Jori Markowski, and Joni Teravainen, using these sieve ideas and no Riemann zeros. And it's actually very elegant. So this is a very much simpler proof than ours, I have to say. It's really lovely. It's a little off the subject, but I thought I'd bring it up. And then perhaps the biggest breakthrough using the sort of new philosophy was a paper of Kaisa and Maxim Rajevu. It came out in 2016. And the idea was to look at multiplicative functions in very short intervals. And what they showed is if you take a multiplicative function that's 1 and minus 1 frequently enough, then so you'd expect if you go in this interval of length 100, there should be some ones, there should be some minus ones. And essentially they prove that. I'm modulo all the technicalities. And this is a revolutionary theorem because previously the length of intervals you could prove something like this in was like x to the 1/3. And now they basically proved it in a long enough interval, L sufficiently large depending on epsilon and f. So it's changed the face of number theory, in fact, this result. And there are many applications. You probably heard some of them. Tao fairly quickly saw how to solve a famous old problem of Erdos, the Erdos discrepancy problem. I should say this interval length, one thing I was quite interested in is whether they could prove something like this for sums as two squares in intervals, and they did because they're a little less dense than integers. And I guess the most popular application of this family of ideas is to look for sign patterns in this. Remember, lambda was the function that's -1 to the number of prime factors of an integer. So if I said to you, I want n such that n plus 1 has an even number of prime factors, n plus 2 even, n plus 3 odd, n plus 4 even, can we find a lot of such integers? And this has been a major topic of interest because I can't get into it, but it's quite closely entwined with the twin prime conjecture. And Terry Tao, Joni Teravainen, in fact, Kaiser and others have been working on this and generalizations of this. And in fact, more generally on sums like this, where all these FIs are different multiplicative functions, and whether or not one can get some sort of non-trivial pound on this. So I really haven't got time for all the things I wanted to say, but suffice to say, it's a very hot and exciting area of research. And it's not quite clear what the near future holds, but a lot of interesting results. So another area of interest here is random multiplicative functions. So if you pick f of p of -1, 1, each an independent random variable with probability of a half, and what do you expect the sum of fn to look like? Well, you could sort of model it on if you just had everything was an independent random variable, not a multiplicative function, where you've got central limit theorem, so it's normal distribution of mean 0, standard deviation, square root x. And I think the best guess was that multiplicative functions probably are like that because we don't know anything better. But in fact, and I should say one consequence of a central limit theorem is that the sum of xn should be of size roughly root x most of the time. Something that didn't happen in the polls in the recent US election. They were far too close for it to seem real. But anyway, let's not get into that. So Harper showed amazingly that this couldn't be normal. The standard deviation is easily proved to be root x, but somehow he used the martingales to show that fourth moments can't work. And let me just say what he did more recently. is that I had thought anyway, foolishly, that the sums would probably still be around size root x, whether or not there's a normal distribution. But it turns out to be quite wrong. It turns out that they're weirdly smaller by typically a log x for the quarter. And this is quite a deep proof. It comes out of ideas from random walks and probability theory, which I haven't got time to go into, but rather exciting result, a surprising result. And quite recently, I don't know if you heard in probability theories, this law of the iterated logarithm to understand sort of a maximum like this. And recently, this maximum has been computed. And again, it's not really what you'd expect from something that looks like central limit theorem. So there is this interesting question of what this distribution looks like. We can also look at random multiplicative functions on the unit circle. And then there's a close tie-in, because as you take the expectation, you get something that looks like this, which is a truncation of the Riemann zeta function. So with the correct normal, because this is true for all integer moments, you'd expect these to have the same distribution function. So to understand this, it's interesting to understand truncations of the Riemann zeta function. And obviously, if you take this to the limit, you have something that looks like zeta. You have to be a little bit careful when sigma is less than 1. But looking at this in this sort of way, there's some recent very interesting work by Saxman and Webb at University of Helsinki, who linked this to the complex Gaussian multiplicative chaos distribution, and therefore to theory of log correlations and random walks, and related to Adam's work, Adam Harper's work from the previous slide. And this is a very hot topic at the moment. Okay, so I just recently was looking with some collaborators at this question of, if it's not normal, what is it? And we think that the distribution function looks something like this. What I should say is, this is consistent with everything we know. It's not there's nothing quite proved. But what's interesting is you get this, and in the normal distribution, you get something like e to the minus tau squared over the twice the standard deviation plus some mess. And here we have something extra that doesn't seem to go away. So there doesn't seem to be a practical way to shift this away. So we get a distribution that looks sort of like normal distribution, but isn't. It's very mysterious, really, what it is. And this, I should say, this is probably correct for large values, but not for small values in the way we've gone about it. Anyway, okay, so let me ask another question, which is, in this work with Soundarajan that I did, we looked at multiplicative functions that take values plus or minus 1. And we saw the mean value lies between this strange number, minus 0.656999, and 1, and that every value in between is attained. We call this the spectrum. And you can ask, what happens if, instead of picking f of p to be a square root of unity, why not pick a cube root of unity or a fourth root of unity? So, oh gosh, I see my time and I really shouldn't get into this. Let me not get into this. Maybe I should say briefly that we're able to transform this problem into something about integral delay equations of this sort. This is like a Volterra equation. Let me not get into it. Anyway, let's just focus on this cube root of unity. So it's a bit harder. Why is it harder? Because when I take the mean value of something that's real, it's just a real number and it's going to be on the real line. But when I take the mean value of something that lives at the cube roots of unity, it could be anywhere inside the convex hull of the cube roots of unity. So this is some work with Kevin Church. We try to compute what are the possible values. And here, well, you have the unit circle. Here we have the cube roots of unity, or the outer shell of the convex hull of the cube roots of unity. And this line, and inside it, is where the mean values live. You can prove the mean values must fill in the box inside. But we haven't, it actually turns out we're not able to identify precisely what this is, or we can each point, but we don't quite know what this whole curve is. So one can do similar things for the fourth roots of unity. So this is all multiplicative functions where the FP is a fourth root of unity. What are the mean values? You can see it wants to hug the box of the convex hull, but it's sort of nicely curved away in different places. And here's fifth and sixth roots of unity. Okay, let me move on from that. I'm breezing through a lot of different questions here. So the cube roots of unity, if you take some multiplicative function that's defined in cube roots of unity, then it's inside the convex hull of cube roots of unity. But you can ask, what's the most negative point you can have? And I mentioned earlier that you can think of plus or minus one multiplicative functions in terms of the Legendre symbol. So another way of interpreting our result is that if you want to count how many squares there are on P up to X, then the minimum proportion is 1 plus that 0.656999 over 2. Okay, because if you just think about it, that's what it's giving, which gives you about 17% of squares. That's the minimum. So you can ask us similar questions about cubes. You can say, well, if we take all of the FPs amongst the cube roots of unity, what's the minimum number of times you can hit 1? And, well, Kaiser and I worked last year when I was visiting Turku on this. And we hope we can prove something like the following. If f at primes is amongst the kth roots of unity, then the minimum value looks like some strange constant to the k times rho of k. Let me explain. Rho of k is a well-known constant in number theory, which is the probability that a random integer has no prime factors bigger than n to the 1 over k. And then, well, this is sort of a trivial upper bound on this minimum, this rho of k, but we somehow beat it by this. It's the result of some calculation. What's interesting is that what we think we hope to prove is that the only way you can get the minimum is if our function actually looks like 1 for a while and then a kth root of unity, a primitive kth root of unity. So if you remember in the case of Soundarajam, when we did k equals 2, it was 1 and minus 1, and it seems that generalizes rather nicely. Anyway, this is still work in progress, and it turns out the main part of his proof boils down to a lot of additive combinatorics, rather strangely. Okay, one more result, or the family of results. So in 1949, Selberg was interested in a multiplicative function that's alpha on all the primes. And so what he was able to prove is this rather strange result, that the mean value looks like log x to the alpha minus 1 over gamma alpha if alpha is not a negative integer or 0. If this was 0, if f of p was 0 on every prime, then this would be 0, except that n equals 1. So the mean value would be basically 1 over x. So it wouldn't look like this at all. So at alpha equals 0, you couldn't have this formula. It would be 0. At alpha equals minus 1, then I'd have here minus 1 to the n, minus 1 to the omega n, which is lambda n. And we saw in the Riemann hypothesis, we think that that looks like root x, so divided by x, that would be 1 over root x. So again, at alpha equals minus 1, we don't get something of this form. Now, what I should say is that alpha equals 0 and alpha equals minus 1 are poles of gamma. So it is actually consistent with this, but we actually get some sort of very different looking mean value when we have integers here. So the proof of Selberg extends fairly easily to functions which are alpha on average, in some meaning of the word average. And let me give you one example, which are integers the sum of two squares. If you've done an elementary number theory course, let me not try and explain everything there. But basically, if you have an integer the sum of two squares, its prime factors are either 2 or congruent to 1 mod 4. They're usually not congruent to 3 mod 4. So basically half the primes, because the primes are 50-50, half of 1 mod 4, half of 3 mod 4. So the density of primes here is a half. Or if I score 1 on every prime that is 1 mod 4 and 0 on every prime that's 3 mod 4, then the average is a half. And so up here, I'd expect a half minus 1 over gamma of a half. And that's essentially what you get here. This was actually proved before Selberg by both Landau and Ramanujan. this formula for number of sums of two squares up to a point. I should say that making it flexible like this is due to a Frenchman, Deslange, a few years after Selberg. So I recently wrote a paper, actually, where we just noted that Landau had, in some sense, done the first analytic proof of this type. Then Selberg did his brilliant work like this. And then Deslange made the method more flexible. So we called it the LSD method, just a little bit as a joke. So if you want to get over 1,000 downloads of your paper, call your paper the LSD method. It's actually now in the, not only in MathSciNet and Zentralblatt, it's also in all the medical academic references too. They just saw this title and assumed it was a medical paper. I hope no LSD researcher goes to it and tries to understand what on earth's going on. Anyway, so what I should say is that Selberg's proof of this involved the Hankel contour, where you go around some sort of pole, but the right way to do it is to come in from here rather than more normally, I guess, which would be to integrate to the right. So a question I've long been interested in for various applications is where you have a multiplicative function that's one value and then another value later on. And we saw in this work that with Kaiser that we had something that was 1 and then a k through the unity. So analyzing that function actually is pretty difficult. And when I look at this, if I look at the mean value up to any x less than y, then I'm just in the Selberg case. And it turns out if I look at the mean value up to any x, which looks like y to the u, then I can use Deslange's modification of Selberg and get some asymptotic from the mean value. So the real question that's interesting is, what is this mean value when you're at y to the 5 and y to the 10? What does it look like? And well, let me just show you, because I haven't got much time. I'm just going to show you what I should say. What the literature has is I talked a minute ago about integers that all their prime factors are bigger than the integer to the power 1 over k. Well, that involves this function, that is where alpha equals 1 and beta equals 0. And in sieve theory, there are various examples then where alpha equals 1 and beta is between 0 and 1. But in fact, when beta is negative, I'm not just talking about real numbers here, there's basically no work except the work I did with Soundarajan, which would be the case alpha equals 1, beta equals minus 1. And there we just found the absolute minimum. So what I did recently with Kevin Church was to graph these functions. So here is the function that starts as 1 and then becomes minus 1. So its mean value is 1. And then as the f of p is a minus 1, it goes shooting down until it hits that minus 0.656999. I mean, it crossed 0 at this little circle. And then it comes back up and it tries to get to 0. And then it's closing in on 0, but never reaches it. This actually gets, it goes at a very fast speed towards 0. If I look at different values of k, so I just have f of p as k and then minus k, I can draw a similar graph at 1.5. And I go below 0, I go above 0, so there's 2 zeros, and then it goes fast towards 0. If k equals 2, there's 2 zeros. K equals 3, there's 3 zeros. And then again, after the last 0, it very rapidly tends towards 0. Here's k equals 5. You can see 5 zeros. You can sort of see a pattern. K equals 2, there's 2 zeros. K equals 5 is 5 zeros. K equals 5.5 is 6 zeros. K equals 6 is 6 zeros. So what we can see from the data is that the number of zeros of this function, so this is again the mean value of f of n, where f of p is k and minus k, it appears to be the integer greater than or equal to k, that's the number of zeros. And if you look at these graphs, they look almost equally spaced, the zeros. We can look at the decay here, and it turns out when you look at this more finely, the decay at 5.5 is much slower than the decay at 6. And in fact, when you really analyze it, it looks something like this. And then finally, the global minimum seems to occur at the first minimum. So this is a project that on the second part of my sabbatical, I went to Stanford and worked with Soundarajan, and we more or less prove all these statements. So we can more or less understand these graphs. And let me just finish with, for those of you who are analysts. So it took us a while to prove this, but of course, you do a lot of work and then you find the right way to think about it. And it turned out that our contour integration, I remember Selberg used the Hankel contour that went all the way to infinity here. It turns out for us, there are two saddle points. And what we have to do is sort of completely change direction at the second saddle point and come here. And then we get a formula that looks like this. So remember, I had different phenomena where k was an integer and k was half an integer. So you can see when k is an integer, this term disappears. And I only care about this saddle point from the cosine. And when k is a half integer, this term disappears. And I only care about this saddle point. So, okay, well, that's some sort of survey of recent work on the subject, and I'll finish there.